Hello again. The last time I left this, we had one flashing light on pin D0, an output pin obviously, another output pin with another LED on D1, and an input pin connected to the switch on D2. And we pressed the switch and we light the light. But I introduced Morse and transmitted manually the word "the." And I wanted to change the functionality so that when I press this switch, we'll transmit using the LED the pattern of dots and dashes that would have made up the word "the." Now, obviously, the light bulb was never used in Morse sets. It would have been electromechanical devices, because Morse was used long before the light bulb was invented. I think the light bulb was probably used at sea for Morse code, but that was it. So we want to create an API here for this Morse. So I'm just going to transmit one word. So it's not a good API. APIs are good. APIs are the most important thing, probably, or one of the most important things in programming. I mean, readable code is obviously probably top of the list, but APIs are not to be underestimated. They're a good abstraction of functionality, low-level functionality or protocols. A good abstraction is hugely important. For example, the internet protocols, TCP/IP, they were invented in the late 60s, and it would have been a struggle to write a piece of application code which made use of that network until Berkeley's Socket Stream API, which gave an abstraction of the network layer so that an application could very simply create a piece of code that used that API to transmit and receive across the internet, which produced an explosion of functionality and the client-server architecture of the 1980s, which was the buzzword for quite a while. Today a lot of stuff is written in Python, so we've got a higher level and we don't see that API, but that API, I'd say, underlies an awful lot of functionality. Similarly, printf, that is an API for displaying characters that was invented with the C language in 1970s, so it's been used millions of times and will still be used millions of times. We'll get to it in due course. So a good API, this isn't going to be it, because I just want to illustrate some things, some functionality. So this is the line of code here that sets the output pin on D1 given what is read from the input pin on D2. So we're going to change the functionality, and instead of that, we're going to say if we read back 0, then we want to transmit the word "the." So we'll just create a function that transmits "the." This is going to be one function API, and it's not very good because it enforces a policy. APIs shouldn't really enforce policy, but this is enforcing a policy whereby the only word that you can transmit is "the." It's kind of useful in very limited situations. So in C, this is my directory with the project in, so I'm going to create morse.h, which would be where we define the API, and create morse.c, which is where we implement it. Usually, I could create a new source file using the IDE, but the last few times I've done it on this, it's kind of messed up and confused the IDE. So I've just created on the command line and come back to here and include it. So we're going to include our API. and we can't open that file automatically because I have no idea. There it is, happy now. Right. So this is the file that defines as external our new API function, which is Morse tx the, and it accepts no parameters, so it's void, and it returns nothing to the caller, so it's void. And that's exactly the implementation we have, the calling nature we have here in the main function. So if we compile this now, you can see that the main compiles, but the linker is complaining that there's an undefined reference to this function that we've defined. So back to morse.h, we'll just copy this and we're now going to implement this API function. And we need a delay. So we had a delay macro at the top of our main.c, but it's not being used, so we'll strip it out of there and paste it back into morse.c. Now it's used, we'll need the trick include file xc.h for the compiler to pull in the definitions, because we're going to be playing with the port with special function registers defined for the microcontroller we're using. We also need a delay variable that's used in this delay macro, so we'll define delay. That's not been found, the definition of a uint32. In embedded systems, we don't tend to use definitions, compiler definitions like long or int or short. Those are compiler defined definitions, which are the length and the storage space associated with those is defined by the compiler, and it's going to be compiler and underlying processor dependent. So they're very non-portable. So you program for defensively. Ultimately you're probably going to move this code to a different processor, so you would never use short in an embedded system. You'd always use these definitions. So that's an unsigned integer 32 bits long. No matter what platform you go to, no matter what compiler, it's going to be 32 bits of an unsigned int. To get to it, we have to include standard int.h. If you spell things right. So we need that both there, and we need it in Morse. So to perform this functionality, we're going to break this into a number of functions. So we need to be able to transmit a dot. We need to be able to transmit a dash. We need to be able to transmit the end of character and the end of word. And given those functions, then to transmit the word the, we need to transmit a dash. We need then to transmit end of character. Then H is 4 dots. End of character. And then finally a single dot for our E. And that's the end of the word. Oops. So all we need now is to just implement these 4 private functions in this file. So declared static, and all we need to do is set, we're working on pin 1 of D, so we want to set that to turn the LED on and then delay. Turn the LED off and delay again. And the functionality for a dash is similar. We want to turn the LED on, but we want to delay for 3 periods for the length of a dash. Now the 2 delay functions, they only delay. They don't transmit on the or change the value of our register or port D pin. So the end of character delay is 3 periods, but we're transmitting a delay, a single delay for the end of element on the end of a dash and the end of element on the end of a dot. So we only need to add 2 more delays to get the end of character display. Similarly for the end of word, which should be 7, we only need 6 delays to make up the end of word. And that's the functionality we need for this API. The interface, just one function into it, and we're calling it when the switch is pressed. So if we just plug in a programmer, and we'll reflash this. And if all has gone well, we still have a flashing LED. But now when we press the button, we should get a dash, end of character, 4 dots, that's the 4th, and then the end of character delay, and now a single dot for the E, and then the end of word delay. So that's all working insofar as it's doing what I said it would do, but there's one problem with this code, which is it's written in an asynchronous manner, or sorry, a synchronous manner. And there are 2 words that are used a lot in computer science and in various different contexts. In this context, a synchronous program, this is a synchronous program because it's going 1 step at a time. The processor is doing one statement, executing one statement, executing the next statement, and so on through the code, the program that we've written. So as soon as I press the LED, I'm doing what I've said. I'm transmitting the word "the," but I've locked out the other LED that is supposed to be flashing, because we're operating in a synchronous manner. And it's not until we finish transmitting and we finish that task that we will resume flashing the LED at the end of that block of code that we're trying to work on there. Now this asynchronous synchronous codes is not it's not peculiar to an embedded system. If you were programming for an Android device, Google have certain standards and templates for how you write stuff. But if you wanted to download a block of a big file from the internet, which is going to take a long time, you don't want to start that task and lock the user interface, so that now the touch screen isn't working and people are banging on their phones and it's not responding because it's downloading a big file, and once it's got that done, I'll come back to you. That's unacceptable. So what you do is you write code in an asynchronous manner. Now there are different tools and tips and tricks, I suppose, to do that on the various platforms. If you're on Android running on Linux, then you've got threads, you've got processes, you've got numerous ways of creating things that run in the background or run in parallel. In an embedded system, we don't have that. We could write a scheduler if we wanted to, but we're not going to be doing that today. So this goes through the synchronous nature. It goes through step, and normally it steps over this API function that we've just written and doesn't enter there, and goes back up, goes through this count to turn the LED on and off, and goes through. But once we press that button and we go into this function, we're stuck in that function and we're not coming back until we've transmitted the word "the," or whatever it is we're transmitting. We could be transmitting twice as many or 3 times as many. It's a finite period of time which we're going to be trapped in this function. So we want to write this in an asynchronous way. And to do that, at this level, like the very rudimentary level, and even though I say rudimentary, these fundamentals are what even a high-level piece of code or a high-level architecture like Linux would be using very deep down. So in our microcontroller, we have a single ALU. That's the arithmetic and logical unit. All that does, as the name suggests, is a bit of arithmetic and a bit of logic. That's all it can do. But it goes through step through code, and that's all it can do. Inside the silicon is a timer block, which is a separate piece of silicon. And we've been using special function registers, what Microchip calls special function registers, to mess about with port D. But we'll use special function registers to configure our timer block, to configure a timer, and then when the timer expires, it will send an interrupt back to the logic unit, the arithmetic logic unit. When that happens, code runs. We go to another block of code, a very short block of code, and then back to where we were, and the logic unit carries on. So there's going to be a short delay in here when we're overdoing this piece of code, and this is our interrupt service routine, and that is going to be what we're going to use to change the code to be asynchronous. Now this, even though we're doing this, we're given the illusion of asynchronous. The ALU is always stepping through code, one step at a time. But we're going to use timers, so we're going to start using this timer block in the next episode. But for the minute, simply there. Thanks a million for watching.